We here at Prime Movers Lab are excited about the future of high-speed flight. Modern multidisciplinary design and optimization tools and high-performance computing are helping to enable today's high-speed flight renaissance. We expect to see commercial supersonic and hypersonic flight tests in the next 1 to 3 years. And by the end of this decade, you'll be able to fly supersonic commercially. Hi, everyone. I'm Liz Stein, a technical partner here at Prime Movers Lab. My background is aerospace engineering, as you can see behind me, and today I'm going to explain the physics of aerodynamic design. Anything man-made looks the way it does for a reason. Subsonic aircraft, like the 737s we all fly around in, are round, smooth, and continuous to reduce flow separation and minimize shear viscous drag. Supersonic aircraft, like my SR-71 model here, are sharp, and we do this to keep the shock wave attached. This minimizes the pressure drag on the vehicle. Hypersonic aircraft, things flying at faster than Mach 5, like my space shuttle model here, tend to be rounded, and we do this for survivability of the aircraft. We take the increased drag penalty because the strength of the attached shock wave would melt the materials of the aircraft. A little bit about the fundamental flow physics for aerodynamic design. Form determines the function. The shape of the vehicle dictates the velocity and the pressure fields around it. These variables are related to each other through the conservation of momentum. For fluids, that's better known as the Navier-Stokes equations. These equations have terms to describe the pressure forces and the shear viscous forces of the boundary layer. We integrate those forces over the surface area of the aircraft, and we break them down into the resultant forces of lift and drag. And efficient aerodynamic design maximizes lift while minimizing drag. A little bit about the physics of shock waves for supersonic flow. A shock wave converts kinetic energy from the flow into increased static pressure, temperature, and other loss mechanisms, such as the sound of the sonic boom. And for hypersonic flow, things like thermochemical non-equilibrium, chemical reactions of the air, and electron stripping. The speed of sound is a function of the fluid properties and the free stream temperature of the flow. At 45,000 feet, Mach 1 is about 660 miles an hour. It's pretty sporty. So why do we want to have attached oblique shocks for our supersonic flow? The example I'll give you is, let's assume we have an aircraft going at Mach 1.7. For an oblique shock, it's a weaker shock. If we turn the flow at about 17 degrees or less, so nice and sharp leading edges on our wings, we can have the post-shock environment still be supersonic and greatly reduce our pressure drag on the vehicle. For a normal shock, you end up getting a post-shock velocity of about Mach 0.6, 0.64, which is even slower than what we travel in for our conventional subsonic 737s, which cruise at about Mach 0.8. So you want to have oblique shocks for supersonic flow to be efficient. Now, I mentioned for hypersonic flow, we round things out and we actually want the normal shock. Why do we do that? It's because hypersonics is hot, like really hot. So hypersonic flow is non-ideal. The air molecules slam into each other so fast, they no longer bounce off of each other like ping pong balls. Rather, that collision energy is greater than the activation energy for a chemical reaction. So you end up breaking the bonds of the molecules and getting this essentially reacting soup around the aircraft. As you go faster and faster we start seeing chemical non-equilibrium around Mach 7-ish. As you go faster above Mach 10 into 15, 18, you end up getting essentially weakly ionized plasma around the aircraft. So how hot is hot? At Mach 2, your post-shock temperature is about 400 Kelvin. Not bad, most metals can handle that just fine. At Mach 5, it's about 1400 Kelvin. You need to have fancier materials then, things like Inconel for that environment. At Mach 15, your post-shock temperature is about 6000 Kelvin. There isn't really anything in our conventional materials that can survive that, so we end up going to things like ceramic tiles for the space shuttle or ablative materials like every reentry capsule that's out there. Additionally, the mathematics to model hypersonic flight end up becoming more complex with thermochemical non-equilibrium. So our matrices that we have to solve are very stiff, it's much harder to converge, and we would love to rely on test data, except our ground wind tunnels can't represent the full physics of flight. That means the only way to get there is to fly. The future is faster.